back. You're back with me. Okay, why you came back, I don't know. But I'm teasing. So here we go. Let's look at the forces that you feel when you're going around. The bobsled track contains a turn with radii 33 meters, 24. Find the centripetal acceleration each turn for a speed of 34 meters per second. Express answers as multiples of g. Okay, so if they're flying around here and they hit here at 34 meters per second, all right, so we're just trying to find the AC. We're not worried. So there's a centripetal acceleration going in, and there's also a gravitational force that's pulling them down this way. But those calculating those forces gets way beyond the scope of this course. All right. So here you go. AC 34 meters per second squared over 33 meters, 35 meters per second, 3.6 G. Where the heck they get that? They divide by 9.8. That's how you get a G. All right. 1G is 9.8 meters per second squared. 2G is 19.6 meters per second squared. Look at this. 4.9 G's as the turn gets tighter, that centripetal acceleration gets stronger because they're actually making that turn. All right. Now then, if you recall, all right, so now, when a net external force acts on an object of mass m, the acceleration of results is directly proportional to the net force. Okay, that's all Newton's second law. Now, so the centripetal force is equal to MAC. The centripetal always points toward the center of the circle and continually changes direction as the mass moves. It is the net force as you're going around a circle, going around a turn. Okay, the model airplane has a mass, so that's pretty straightforward. Nice, good stuff. Trapeze act hangs upside down from bent over the holding his partner. Is it harder for the man to hold his partner when the partner hangs straight down and is stationary, or when the partner is swinging through the straight down position? That's interesting. Let's figure out. Let's answer that question real quick. I think that's a good question. So let's take a look. All right. So if he's just, where are the forces that we're looking for? It's hard to hold. All right, so he's holding on to the partner. So how much force does it need to hold this partner up? Okay. In other words, what's the force? All right, so let's see. I don't know. So let's analyze the forces. All right, so if he's just hanging there, all right, so he's on his little trapeze here, and he's got his legs kind of hooked over here, and his head's going down here. He's got his arms out like this, and he's holding on to her here. Okay, and she's got her arms up like this. All right, supposedly that's trapeze. All right, the action-reaction force that he feels, she's pulling down, F of G, mg. That's the only force that he's having to hold up there. Now, his knees up here, ouch, that's like m1g plus m2g. That's pulling down. So the normal force that he feels here is m1g plus m2g. Ow, that hurts because it's got to counteract that because he's not accelerating in the y direction. Neither is he accelerating in the y direction here. Now, let's just look at it as if, let's just put the trapeze here, and let's look at the tension force. All right. So here's the man, here's the woman, and she's swinging by with a velocity v. All right. There's the tension force. Here's the force mg coming down here. All right. The tension is what's in his arms. It's what he's feeling in his arms. Okay. So here's the woman. All right. T is equal to, now, net force. Sum of the forces in the y direction is now equal to a net force, MAC, which is equal to the tension that he feels in his arms minus mg. So therefore, MAC plus mg is equal to T. It's harder when she's moving. Okay? because when they're just stationary, sum of the forces in the y direction is equal to 0. There's no acceleration upward. So it's just the tension in his arms minus mg. And I consolidated the tension. It'd have been a T1 and a T2 going straight, whatever. It'd be 2T minus mg. It still doesn't matter. All right? So that's interesting. Now let's look at bank curves and we'll call it a day.